Hi, this is Prasad. This is final project presentation on topic comparative analysis of 3D point clouds for spherical, cubic, and botanical objects using structure formation in LiDAR. Objective is to evaluate the quality of point clouds for 3D modeling of objects using SfM and LiDAR. Objects studied here: Rubik cube for planar, and orange for curvature, and plant for complex structure for 3D modeling. Sony A6000 for SfM and Intel RealSense L51 for LiDAR were used. Cloud Compare and AgiSoft and Open3D were used as for analysis. Calibration is performed on markers with accurate measurements. A mean projection error was at 3.38 pixels for Intel was obtained in MATLAB. And similarly, Sony A6000 camera got mean projection error of 0.16 pixels. The datasets were collected in control indoor settings, like no external variables, like similar lighting conditions. We can observe this in this picture, like an object of interest was placed on a stationary table where the camera mounted on a rotating arm rotates around this object 360 degrees at different speeds, and the speed levels are controlled by an Arduino setup. At 10 rpm and 30 rpm, these methods are performed. At 10 rpm, nearly 160 images were collected, and 30 rpm collected like 78 images, and more than 30 rpm speeds, the images were having less than 50% overlap, so which leads to misaligned point clouds. Similarly, RealSense camera was mounted on this rotating arm. Since the camera collects point cloud directly, I have rotated around this and collected 4 point clouds for each object. After the point clouds are collected, these point clouds are subjected to statistical outlier removal to remove most of the noise. And SfM at 10 rpm, point clouds are taken as a reference or ground truth and compared with other point clouds. Cloud to cloud distance were measured, like mean distance, RMS, standard deviations. Volume histograms were computed, and quality inference was performed for ranking these different point clouds according to their density and accuracy. SfM seems to be working good for cube and orange, and similarly the point cloud of plant seems to be also working good. As when compared to Intel RealSense, the point cloud for cube seems to be very distorted, and orange seems to be noisy, and similarly the point cloud for plant seems to be very noisy. So the comparing the results in a tabulated form, like SfM at 10 rpm stands out compared to rest of them. For orange, surprisingly, SfM at 30 rpms performed well compared to remaining point clouds. For plant, SfM at 10 rpm seems to be working good. For LiDAR, the point cloud seems to be not at all working. Here it's very noisy. So comparing the volume density distributions for cube, the distribution seems to be uniformly spaced. But for LiDAR, there are less number of points compared to the SfM. 10 and 30 RPMs. When compared to our orange, the LiDAR seems to be very distorted. For plant, SfM at 10 and 30 RPM shows some spikiness, uh, and also the LiDAR performed bad here, like they have very few points. The key takeaways are like SfM at 10 RPM excels for complex objects like plants. SfM 30 RPM performs best for simpler objects like oranges. LiDAR struggles across all objects, especially plants, due to sparsity and distortions and challenges and findings. LiDAR's high point cloud for the cube is misleading due to noise. Faster rotation improves coverage for smooth objects but reduces quality for complex ones. Future work, computing surface roughness to quantify noise in LiDAR data, and explore hybrid SfM LiDAR approaches to improve alignment, and test on more diverse objects for reflective surfaces and experiment on different lighting conditions. Thank you.